Hello, everyone. Today I'm going to introduce our work entitled Is Chain-of-Thought Reasoning of LLMs a Mirage, a Data Distribution Lens? Recent years have witnessed large language models' dominant role in various domains through versatile prompting techniques. Among these, chain-of-thought prompting has been shown to be very effective for eliciting structured reasoning from LLMs. By simply appending a simple cue, let's think step by step. The larger models are able to break down the question and output the intermediate process before arriving at the final answers, which leaves an impression that LLMs are involved in the thinking process or the reasoning process, just like humans. However, a closer examination reveals inconsistencies that challenge this optimistic view. Let's consider this question. On which day of the year was the US established? In a leap year or a normal year? When we use this question to prompt Google search LLMs, it outputs the results like the following. As you can see, the intermediate process is perfect, while the final results are incorrect. Such inconsistency may suggest a distinction between human reasoning and LLM's thinking. Moreover, a growing body of research suggests that LLM's reasoning may be more superficial than it appears. They witness LLM's reasoning fail in planning, puzzles, and complex mathematical problems. Scientific research builds upon the foundations laid by previous giants. Each of these pioneer work represents an empirical contribution to what we term the mirage of LLM reasoning. Like Plato's allegory of the cave, the shadows we perceive may be partial and empirical representations of a deeper reality. It motivates us to research further and explore the nature of Coty reasoning. Therefore, in this work, we propose a perspective, a data distribution lens, to study and understand the Cote reasoning. Specifically, we think Cote reasoning reflects a structured inductive bias learned from in-distribution data, allowing the model to conditionally generate reasoning paths that approximate those seen during training. Thus, its effectiveness is fundamentally bounded by the degree of distribution discrepancy between the training data and the test queries. Our work reveals that underlying this empirical mirage is the distribution lens that is the theoretical foundation. This framework demonstrates that the failure or success of LLM reasoning is not coincidental, but rather predictable. Let's provide some theory intuition first. Given the training and test distributions, we define the distribution discrepancy as a divergence measure. Based on it, we try to find the boundary for Coty generalization. The effectiveness of LLM's reasoning, that is, the expected test risk, is less than or equal to the expected training risk plus the distribution discrepancy plus a constant. In practice, we can estimate the expected training risk using the cross-entropy loss for next token prediction. Here, the first term is determined by the model's capacity, which is related to the size and architecture. For example, if we consider a state-of-the-art model like GPT-5 or Gemini 3 that fits the training data well, the expected training risk is relatively low. But even this, the code effectiveness is still dominated by the second term, the distribution discrepancy, that is our data distribution lens. Guided by it, we identify three critical dimensions along which distributional shifts can occur. The task dimension examines the extent to which Coty reasoning of LLMs transfers across different reasoning tasks. The length dimension investigates the robustness of Coty reasoning across chains of varying lengths. Format dimension explores how sensitive Coty reasoning is to variations in prompt formulation and structure. This refers to the fact that users in the real world cannot design the gold prompt for LLMs, because the golden prompt only resides in the training data. Then the next question is, how to validate empirically? Evaluating on-the-shelf SOTA LLMs without training may be appealing, but two problems appear. Firstly, the containment problem. LLM weights are open source, but training data is usually not, which makes it very difficult to directly assess the extent of our data distribution. Secondly, a complex problem. Companies' LLM training uses almost all available online data, which introduces confounders and makes it hard to isolate the factors underlying distributional shifts and to scientifically and rigorously investigate them. The opacity and complexity of their training data would preclude drawing generalizable conclusions. To use an analogy, one cannot conclude that a feather and an iron ball fall at the same rate by testing them in normal air rather than in a vacuum, because the complicated surrounding conditions, that is to say, air resistance, would obscure the true law of gravity. Therefore, we need a clean control environment to eliminate contamination, isolate spurious factors, probe Coty reasoning, and further investigate its true nature. In this work, we present data alchemy. It creates an isolated, controlled environment for training LLMs from scratch. It allows us to manipulate the training data distribution, test cases, LLMs, and almost everything, and systematically probe LLMs to produce Coty reasoning under different conditions and validate our theory. Data alchemy environment encompasses various abstract combinations of elements and transformations. representing a microcosm of diverse NLP downstream tasks in the real world. Let's first recall how NLP task looks like in the real world. We can start from the functions LLMs serve. We find that LLMs are useful as annotators or judges. Considering the provided examples, we can obtain the abstract form of diverse NLP tasks. That is, please perform actions based on text. Inspired by these real-world NLP tasks, we use transformations to represent an abstract collection of performed actions and use elements to represent a text collection. In this way, we map and distill the real-world task into a combination of transformations and elements. Specifically, data alchemy consists of basic atoms, elements, and transformations that represent tokens, text, and real-world actions. Further, we can naturally acquire the Coty reasoning step by applying composition transformations and decomposing the intermediate process, thereby providing a foundation for fine-grained analysis. Based on the data alchemy, we design the experiments across 3 dimensions. For task generalization, it further consists of element generalization and transformation generalization. Since the proposed data distribution lens relates to distribution discrepancy, we can further control it by designing the following progressive scenarios. In distribution, ID, where the training and test distributions are identical. Composition, CMP, where the test cases involve novel combinations, partial out of distribution. POD, where the test data involve both novel and existing transformations, and out of distribution, where the test distribution is completely different from the training distribution. For the lens generalization, we divided it into text lens generalization and reasoning lens generalization. Then the distribution discrepancy can be determined by the difference in text length, that is, element length, and the number of reasoning steps. For example, we evaluate the generalization of Coty reasoning from 2-step to 1-step and 3-step reasoning. For the format generalization, we consider the 3 different perturbations to the test data: insertion, deletion, and modification, which simulate the noisy prompts users created in the real world. The distribution discrepancy is the ratio of perturbation. We conduct comprehensive experiments. Here, due to the time limit, we highlight some important findings. In the task generalization experiment, we find that Coty reasoning cannot directly generalize to novel tasks involving unseen elements or transformations, and its effectiveness drops when the task distribution shifts from the training data. Further, Coty reasoning is neither logical nor faithful. Its accidental success is attributed to the replicating pattern in the training data, as indicated by the inconsistency between the reasoning and the answer. During the SFT experiment, we summarized that a small portion of test data in SFT helps Coty reasoning quickly adapt to novel tasks. In the lens generalization, Coty reasoning cannot directly generalize to test cases involving different text lengths or reasoning steps. By systematically varying the training data distribution, we observe forgetting in reasoning with the original lens while adapting to the new lens. During the format generalization, Coty reasoning is sensitive to format modifications. Applying a moderate level of format perturbation will greatly undermine its effectiveness. We also evaluate internal validity. The experimental results show that the data distribution lens holds across models of different sizes and architectures. Further, we confirm its external validity on real-world SOTA LLMs. To conclude this work, our results reveal that Coty reasoning is a brittle mirage that vanishes when pushed beyond the training distribution. This work offers a deeper understanding of when and why Coty reasoning fails, emphasizing the ongoing challenge of achieving genuine generalizable reasoning. Here we provide some resources. Please do not hesitate to let us know if you have any kind of questions. Thank you so much for your valuable time for attending this talk.